warahmatullahi wabarakatuh. So we continue with chapter number 13, part number 2. Okay. So we know that the ion will pass through the membrane from one compartment to another compartment. Okay. So we can generalize the voltage, the different voltage of that membrane using the Goldman-Hodgkin-Gas equation, voltage equation. Okay. So that one is from equation 13.21 from our textbook. Okay, so now we want to know how can we generalize the or adding additional ion in the equation of GHK. So this is GHK. So the flux multiplied by exponential E Z I F V over RT. Okay, so Zi is the national ion charge. Okay, so the flux equal to this one, J equal to minus D. So if we integrate from A to B, these are the membrane. This one is the membrane, not a compartment. These are the membrane of the cell. Okay, the width of the membrane A, B. Okay, so we are going to get uh, this equation. So when we evaluate Vx, so we evaluate this equation, So we use a unidirectional flux by using tracer. So this one we want to say that when we do the experiment, okay, so we can use the tracer. So let's say put the ion with a color, put the color tracer. So the tracer will move either from compartment B to compartment A or compartment A to compartment B. Okay, so then we can measure the flux of that ion. Okay, so if the tracer is added to compartment B, so we can see the equation of that flux. Okay, so the ratio of two flux. Also in this case, the first experiment, we put the ion or the tracer in compartment A, moving to compartment B, and this one we put the tracer in compartment B, moving to compartment A. So the ratio of two flux is J I A B, J I B A equal to C I A C I B exponent Z I F delta V B R T. Okay, so this one these are supposed to be delta V. Okay, delta V, not there is no B here. Delta V. Okay, so these are using flux ratio. So by using this experimental measurement, using tracer flux across frog skin, give a ratio that differed by a factor of several hundred from that predicted using flux ratio because involvement of an active transport. Okay, so even though we say that this one tracer moving to compartment B, and this one tracer moving to compartment A, but if the ion is preferred to be in compartment A, so it will pump out the, even though it already moving to compartment B, so if through the active transport we try to move back to compartment A. Okay, so involvement of active transport. So the dependence of ion flux on metabolic energy was verified by adding a metabolic Poisson. Within a few minutes, the flux changed to value that were in the agreement. Okay. Okay. So what we want to say here is that this one metabolic energy. So if we put the Poisson, so if we kill the ion or the protein and decreasing the concentration of that protein in that compartment, so then the flux will move from the high concentration to the low concentration. So these are the Goldman GHK voltage equation. Delta V equal to minus RT F ln D NA plus K plus K plus. Okay, so these are the concentration and these are the depletion constant for Na, and these are the depletion constant for K, and this one is the concentration of K in compartment B, and these are concentration of K in compartment A. Okay, so if we have zero net current, so the current flux are perfectly balanced by the anion flux, so moving from one side to another side, so equal to 0. Using ratio, so we get this equation, and using the probability or proportional constant. Okay, so we are going to get generalized Goldman-Hodgkin gas voltage equation equal to E cation Pi CIB cation Pi CIA Pi CIA Pi CIB. This one, if we have a lot of ion, type of ion. Okay, so we have magnesium 2 plus, the cation and the ion. So we have so many species. So we can summarize it using this equation. So for the all cation, for all N ion. Okay, so this one express membrane potential as function of concentration and mobility of all monovalent ion by assuming electric field in constant within the membrane, constant frequency. The second assumption, the flux of each ion is independent of the other ion flux. Okay, so this one is the assumption. Okay, so here we can calculate the voltage difference using this equation. So meaning that we can just find the concentration of C, concentration of ion 1 in P compartment and so on. So we do the experiment so we can estimate the voltage. So here for Na plus, K plus and Cl minus, so the membrane potential is equal to, here you can see that, all the contribution from all the concentration of ion, figure 13.7. Okay, and only will fit when the solution being ideal. So because we know that this is not ideal, so we are not going to get a very smooth fit of the experiment and this formula. So when the solution have a different ionic strength, the activity will make a difference, and taking this into account often improve the accuracy of this kind of analysis. So consider this one when we add some more term here. Okay, some more term here, so then we are going to get the experiment is equal to the this theoretical calculation. Okay, so continue with this membrane pump and the potential. So this one is only for passive transport, the concentration, high concentration, low concentration. So when we consider the concentration from the active transport using the pump, all cell membrane contain pump protein. So we have pump protein that harness energy to drive ion against their concentration gradient. Many active membrane pump, most mostly the Na plus K plus ATP phase, are electrogenic and generate a current by pumping more ion in one direction than the other. Okay, so here adding the flux of pump ion, this one J pump. Okay, so we are going to have this the voltage difference. Okay, but by positioning the Na plus K plus ATPase by inhibitors such as osbane depolarize the membrane potential very quickly by 10 to 15 millivolts. Okay, and slower chain reflect the gradual collapse of the concentration gradient in the absence of the pump activity. Okay, so without the pump activity, so there is a small change of the concentration. So this pump in our cell we use to send the signal or doing their function so that the cell can function properly. Okay, so electronic pump. These are the example. In neutrophil, a kind of white blood cell, the membrane potential appears to be generated entirely by a pump. Small contribution from the concentration gradient. Okay, so here entirely by the protein pump. Okay. In mitochondria also have very large membrane potential on the order of 10 to 10 millivolt. These are generated entirely by an electrogenic proton pump. Okay, so here these are the without the concentration. So next we have a transport protein. So this protein move n molecule of n ion from compartment A to compartment B with the counter transport of m molecule of cation B plus from compartment B to compartment A. Okay, so again these are the just like the rate equation, Na plus Mb plus Nab plus Mba plus. So concentration gradient delta G equal to this equation. And the electrostatic energy delta UFE. So solving this, so we are going to get the membrane energy or electrical potential for this membrane equal to NEA plus EB, okay, N plus M. Okay, so this one is, so we have the average of the two nonce potential weighted according to the stoichiometric coefficient of the two ion. Okay, so we can see it, we can plot it using, we can plot this equation. So we are going to get like figure 13.8. Okay, so we can estimate the the transport of one anion or cation through the membrane. So next we have the Goldman GHK current equation. Before this we have voltage equation. So this we have current. So this one when we have a voltage imposed on the ion permeable membrane. Okay, so when we have this outside energy, so it will cause the current to flow from compartment B or to compartment A or compartment A to compartment B. Okay, so these are the current equation. So the internal side of the membrane does not contain small dispersion of charge. The Poisson equation can be written as this one with the solution of the electric potential at x equal to E times x, the current, E is the electric field. Then the equation become this, and integration we are going to get the ionic value equal to this equation, where E Z F B A over RT is factored out, and delta V equal to BB minus VA. Okay, so we can have the concentration of B, concentration of A, the different, and the electric field introduced. So we have this current. Okay, so the Coleman-Hodgkin GHK current equation can be written as this equation. Okay, P delta V, so D equal to P delta V equal to E delta dE equal to V delta V. Okay, so we can measure the current using this delta V, the voltage difference between component A and component B, and also measuring the concentration of ion in component B and component A. Okay, so we can get this uh, current equation. Okay, so if we give current versus voltage for particular ion with different concentration on each side of the membrane, so we have in figure 13.9 in our textbook. So if delta V greater than 0, so I1 equal to this equation, so this one, okay, and when delta V less than 0, so we are going to get this contribution from the concentration in A compartment, this one concentration in B compartment. Okay, so using this equation for measuring the slope I1 and I2, or the current I1 and I2, so we can determine the permeability of an ion. Okay, so how permeate this ion through that membrane. So by contrast, measuring the potential and using the GHK voltage equation, limit 1 to determine the ratio of the permeability. Okay, so the GHK voltage and current equation are constant field equation. Okay, so E is constant. Okay, electric field is constant, so we can get this voltage and this current for the movement of ion from membrane compartment B to compartment A, or compartment A to compartment B. So if we have divalent ion Mg2 plus, okay, so let's say Mg2 plus, so the GHK voltage equation applied only to monovalent. So multivalent ion making solving for delta V a bit more difficult. So we use this CAS, computational algebra system software, okay, to solve the equation. So using a computer, we can find delta V for particular set of permeability ratio. Okay, so here we do some modeling. Okay, so these are the movement of multivalent ion from compartment A to compartment B, or compartment A to compartment B. Okay, so we have this equation. So the membrane potential, solving this one is just x squared minus ax squared plus bx plus c, kalau kita tengok ni. Okay, so this here we can have delta V equal to this equation. So where A equal to this one, B equal to this one, and C equal to this one. So we can get the membrane potential for multivalent ion or divalent ion. Okay, so just using this, putting this divalent ion or concentration in compartment A or compartment B. Okay, so the surface charge and membrane potential, again the repetition. So the surface potential can have a strong impact on the membrane potential. So flux are sensitive to the surface potential. So if the surface potential affect the flux of different ion to different degree, the visual potential will be modified. Okay, so for K plus and Cl minus, delta V equal to this GSK voltage equation. So adding surface charge, okay, for both surface, the Boltzmann division, we have this one. So GHK voltage current voltage equation can we can write it as this equation. Okay, replacing C naught C or C this with this CL. Okay, so we can get the new permeability ratio. Okay, PK PCL RKCL exponential minus 2 F bar per naught over R T. Okay, so by concentrating ion of one sign and depleting ion on another, a surface potential can alter the observed formation property of a membrane of the membrane. Okay, so this one we want to say is that, so when the membrane or the surface only accept, let's say only accept K plus, okay, so Cl plus will be in the compartment, not near the the membrane. Okay, so only K plus will pass through the passing through the membrane. Okay, so we have this ratio. So a surface potential can alter the observed formation property of a membrane. So what we can what we want to say here, or what we are trying to say here, is that when we doing the if we have to do the experiment, okay, so we can manipulate these properties. Okay, let's say we increase the surface uh, through the experiment, we can increase the surface potential so that we can see the permeation of properties of a specific ion. Okay, so we can calculate that, or we can measure the permeation of that specific ion. So the last one here, an ion flux actually depend on how its potential energy varies inside the membrane. So the drop in voltage across the membrane must be added to another force that act on the ion. These other force reflect the interaction between the ion and the membrane, which vary dramatically with position. So these are in figure 13.10. So adding the potential to equation 13.3 in textbook and approximating this equation, so Vx equal x times delta V. So integrating this one, so we are going to get I, or the current, is equal to I equal to ZFP CB exponential ZF delta V 2 RT minus CA exponential ZF delta V over 2 RT. So where P equal to this equation. Okay, so we can measure using through the experiment, we can measure the current. Okay, and from the measured current, so we can do the curve fitting using this equation. Okay, so it's better to see that if we know the concentration of CB CA, so we can find the voltage difference of that membrane. Okay, so that's all for this part, for this chapter.